Hi there, students. Mrs. Brunk again. Today's lesson is about solving linear quadratic systems. So we've spent quite a bit of time over the past few weeks learning about systems of equations, solving them. We also spent quite a bit of time before that learning about quadratic equations. And now we're going to try to put the two things together. And we're going to look at what if we have a quadratic equation and a linear equation that are in a system together. So we're looking for a common solution for both a linear and a quadratic equation. And our essential question is, how can you solve a system composed of a linear equation in two variables and a quadratic equation in two variables? And we're essentially going to look at two methods to do that, the first being graphing and the second algebraic means. So let's jump in. So there are many real-world situations that can be modeled by linear or quadratic functions. We've looked at a lot of them. We've done a lot of applications, especially with linear equations during the systems unit. What happens when two situations overlap? Examine graphs of linear functions and quadratic functions and determine the ways that they can intersect. So examine the two graphs below to consider the ways a line could intersect a parabola. Now, first of all, the linear graph is actually a graph of a constant function. It's a horizontal line. So let's say I were to merge these graphs together, and let's say I shifted that line up or down. So where it is currently, so it could intersect in 0 places, right? So this would be 0 solutions. And then let's say instead the line was, say, shifted up and it was positioned strategically so that it just hit right there at the vertex. I'm just trying to see if I can get it to line up there perfectly. So we're going to pretend like it's hitting right there at the vertex. So it could intersect in a spot like this, and there'd be one solution. And then alternatively, you could have it shifted up here, say, and it could hit in two different spots. And those are really the only three possibilities that could occur, is 0, 1, or 2. There's no line we could draw through there that would like hit, more than 2 times. It's just got the 2 branches on it. So if it hit exactly 1 time, it would be crossing through the vertex, and if it hit none, then it would be either below the graph, as in this case, or if the parabola is open down, it could be above the parabola. Now we could have other scenarios that could occur, so we're going to just graph 3 other graphs of a line and a parabola, one showing an intersection in 1 point and 2 points and not showing any intersections. So the first one in 1 point. So let's say we had a parabola that, I don't know, let's say its vertex was right here, and say it looked like this. Oops. See if I can do a better job on this other branch. There you go. And so we could have a line, say maybe the line's going right directly through the x-axis. Maybe I should have drawn this in a different spot. So let's see, make my parabola so it's not right on the x-axis. That was kind of a specific place to put that. But anyway, so something like maybe this, like that. There's the parabola. And then we have a line that just goes directly through the vertex. And maybe it even goes through the vertex like this. Could even go on this angle like this, right? And it still is never going to cross it again. It just hits in one spot. Okay. Now we could have a situation like where the parabola maybe is opening down, and if we wanted to show 2 solutions, so maybe you have a line that kind of goes like this, and it crosses in 2 spots. And then, of course, similar to the one we saw in the introductory example, just where let's say we have something like parabola's opening, opening up, but say its vertex is right here, like this. Pardon that graph, that's not a very good one. And then maybe we have one that's like, say like this. So it's just never gonna cross it again. So that's 1, 2, and none. No solutions there. So a constant linear function and a quadratic can intersect at, well, it doesn't necessarily have to be a constant. It could be at 0, 1, or 2. So it doesn't even have to be a constant linear function. It could be like, you know, an oblique line like this as well. Or the ones before that where you saw the constant function, the horizontal line, in other words. So the first way we're going to learn how to solve these systems is we're going to look at graphing as a method. And we know that that kind of has its drawbacks. And we'll see if we can kind of incorporate using the graphing calculator in this. But so it says graph each equation by hand and find the set of points where the two graphs intersect. Solve the linear quadratic system graphically. So the first line, or the first one is a line, and I'm going to graph that by just going ahead and like making the intercepts. Maybe I'll put it in slope intercept form, never mind. So I'm going to solve this for y. I'm going to swing the y over here to the right hand side, and I'm going to swing the 3 over here just to make it a positive y. So that'll be y equals 2x minus 3. So I'm going to plot that point at -3. These are scaled by 2, so be careful. -3, and then the slope is 2, so I'm going to rise 2, and I'm going to run 1. Oops. And I'll have a line that looks pretty much like this. Now in order to graph the quadratic, I'm going to go ahead and put this in vertex form by subtracting the 6, so that would be 2 times x plus 1 squared minus 6. Now it's been a little while since we've done quadratics, but remember we can look right at this and tell the vertex. It's at -1, -6, so this is slid 1 unit to the left and 6 units down. And then this is going to be a vertical stretch of 2. So however you decide you want to get other points, whether you put it in your calculator or whether you just, you know, kind of imagine points on either side of the vertex. So the first point is at -1, -6. So let's see, -1, -6, 2, 4, 6. Looks like right about here. Might even be actually where that crosses. And then in order to get some other points, we could, oops, let me get that in the center there. That looks a little better if it's right there. And so say I plug in 0. If I plug in 0, that would be 1 squared, which is 1 times 2, which is 2 minus 6. That's -4. So that would put a point right there. And then one exactly in the other spot. So that looks like some pretty good points. And I'm just going to graph the parabola like that. Now eventually this is going to, oops, so maybe I put another one and maybe I put in 2. So if I plug and put 2 in for x, that would be 2 plus 1, that's 3. 3 squared is 9. 9 times 2 is 18. 18 minus 6 is 12. So this actually, I didn't do a very good job of graphing that because when x is 2, I would be all the way up here at 12, so over 2 and up. Let's see, these are scaled by, it's going to go way above that. It's going to go 2, maybe right up, way up here. So it's going to go like something like this. I think we're already seeing the drawbacks of graphing, right? And then we could put a point at the exact other side. I'm going to try to see if I can graph that a little bit better. Hold on. Actually, it might be easier if I put a smaller number. So I'm going to put 1 in. So 1 for x would be 1 plus 1 is 2. 2 squared is 4. 4 times 2 is 8. 8 minus 6 is 2. So I have the point 1, 2. So that's probably a little easier point to get to right there. We'll just kind of see if we can. And then that means there's going to be 1 on the other side. So if I put, say, -3 in, -3 plus 1 is -2. -2 squared is 4. 4 times 2 is 8. 8 minus 2 is, or 6 is 2. So that would be -3, 2, and that's right here. So what are the approximate solutions? Well, it looks like it crosses right here. That's an approximate solution, and this one right here. But how do we approximate that? Well, probably the best thing to do to approximate something like that is really to use your graphing calculator. So I went ahead and entered the two equations in my grapher, and these are pictures of both the table and of the graph itself. So you can see it looks very similar, except for that this one's not scaled by 2s. And you can see the two spots where they cross right here and here, which is approximately where we found them to be, right? And so they kind of look like they would be sort of near where x would be about -1/2 right here, or 1.5, excuse me, right? And then also one over here where it's between 0 and 1 for x. And if you look in the table, you can see that that means, see between -1 and -2, right? They must have gotten close. And between 0 and 1, it must have gotten close. But there is no place where the two values of the functions are the same. So these are not integer solutions. So the best we could do in order to approximate this with the graph is to use the intersection function on the calculator. And so when we're in class, I'm going to show you how to do that with the graphing calculator. But for now, we just would have to approximate this the best we can. So we're going to wait, we'll hold off, we'll put these approximations in, these two ordered pair, when we're together, and I can show you your graph on the graphing calculator how to do that. But these are not integer values. So that, again, that's the drawback of the graphing the graphing method. So okay, so B, let's try another one together. So this one's going to be, if I put in slope y intercept form, is y equals -3x plus 4.5. So that means the y-intercept is at 4.5. So it's -3. Well, this is going to be terrible to graph because this is scaled by 2. So like the y-intercept is going to be right about here. It's about 4.5. So then we're going to have to go down 3. So that's going to actually put us around 1.5, which would be right about here. And then run 1, which is right here. And then it's -1. So go down 1 or down 3 and right 1. In fact, let me put this a little closer to right there. Maybe right there. So again, this is going to be a real drawback because even how accurate is this graph, because I'm having to approximate even where. So there is the graph of the line. And then we got to do the parabola. So we can do the parabola by, again, it looks like it's in the form where it's vertex form. So, but the vertex is actually at 3, 0, right? There's no here thing being added on the end, so there's no slide up or down. And then that vertical compression by 1/2. So that's the 1/2 out in front. So the vertex is going to be at 3, 0. So that puts it at, there's 2, 3, 0 right here. And it's a 1/2 compression. So normally we go to the right one and up 1, but now we're going to go to the right one and up 1/2. And then to the left one and up 1/2. Like this. And it's going to be a parabola that looks like this. Actually, I should probably get another point just to be more accurate. So normally when you go to the right one, you'd go up 1. So I went to the right one, I went up 1/2. So normally when you'd go to the right 2, you'd go up 4, but that means I'm going to go up 2 instead. So that would put me right about here. Same thing here. If I went to the left 2, I'd usually go up 4, but then I'm only going to go up 1/2 of that, so I go up 2. So that actually puts it right here, and that's a little more accurate right there. So again, to try to approximate that, I mean, I really only see it looks like it's maybe hitting in one spot, but it technically could actually be, because it's not this scaled by 2s, maybe this is like swooping underneath that line, and maybe it's coming right back up, so maybe it's hitting twice. It's really hard to tell. And so we'll use the intersection function of our calculator to show how we can have the calculator find the solution, the intersection point, if there are any, for us. So that means we're actually going to save the solution part of these for when we are able to meet in class and use the graphing calculator to kind of show that process. So all I want you to do for these, for the U-turn, is to just take these and graph them. And you can, I mean, if you want to, you certainly are welcome to put them in your graphing calculator and plot points for the quadratics if you want, however you choose to do it. But just get a preliminary graph, and then to approximate the points of intersection, we'll come together and we'll use a graphing calculator to do that. So I want you to pause the video now and just do your best to graph these. And then we'll tune back in, we'll move on and look at algebraic way, and then revisit these once we have ability to use the graphing calculator functions. So pause the video now and graph these. Okay, so I absolutely used the calculator as an aid to get these parabolas looking good. The lines, you know, you can put in slope-intercept form, that's easy. But the parabolas, you know, once you identify the vertex, and how, you know, it's kind of a little bit tedious to get decent points to put on it. So I just typed them in the grapher, my calculator, and looked to the table, just plotted the nice integer points. And so for A, I mean, it almost looks like this one does have some nice solutions. Maybe we'll estimate this one. I could see that they crossed at 2 spots on this one, so right there and right here. And that looked to be, I'm going to go ahead and put this down and we'll verify once we get our calculator to do that. So -2, -6. And I could actually substitute that in my equations to make sure it works. And then the other solution looks to be like 1, 3. So just real quick, test those. If I plug -2, -6 in, of course that's going to work in the equation for the line. So I plug -2 in times 3 is -6. Plug it into the bottom one, to the quadratic. -2 squared is +4. 4 times -3 is -12, plus 6 is -6, which is, it works. So this one works. And then plugging in 1 times 3 is 3, so it works in the top equation. Plugging in 1 on the bottom, 1 squared is 1 times -3 is -3, plus 6 is 3, so it works in there. So there you go. This one has 2 actually decent integer solutions. So it's not too bad when they are nice integers, but when they're decimals, it's just impossible to just try to get any kind of an accurate solution. Now in the second one, to me, I can't see any possible way these could ever cross. So my approximation is this one's going to be no solutions. They're never going to cross. That line's going to continue at that same rate. The parabola is continuing to grow and very quickly now on the ends. So it's not turning back around, right? So there are no solutions on this one. So in situations like these, you know, there is a way to do that without the graphing calculator. So let's move on and look at algebraic methods. So recall there are 2 algebraic ways to solve systems of equations, and they're substitution and elimination. So elimination is the one where if you can get the coefficients to be exactly the same on one of the variables, or actually we'd rather them be exact opposites, then when you add them they cancel out and then you can just focus on the other variable. With substitution you have to get one equation solved for a single variable and substitute in. Now, in the first example here, I really could go either way, but I'm going to be honest, I actually started this, and I deleted this part of the video. I started doing this one by substitution, and I solved the bottom one for y, and I expanded it all out because I had that square binomial and all that other stuff. And it got pretty complicated, and then I stopped for a second, and I looked, and I said, oh, wait. There's a negative y in the top equation and there's a positive y in the bottom, and those are perfect for elimination. So that's what I did. I'm going to just actually take and flip-flop the 4 and the y around. So it'll be 3x minus y equals 7. And then this one I'm just going to flip around. So it's 4 plus y equals the 2 times the x plus 5 squared. Now when I add, see what's going to happen is just my y's are going to cancel out. So those go. And what I'm left with is 3x plus 4 over here And on this side, I have the 2 that has to be multiplied by the x plus 5 squared, and then the plus 7. So I have 7 plus 2 times x plus 5 squared. Now, this definitely is not an easy equation, but at least it has only x's in it. So now we can start kind of plugging away at it. So first of all, I have this that I can expand out. So when I expand that out, and then I'm going to multiply it by 2. So that's x squared. If there's an x plus 5 and another x plus 5, then I FOIL it. So that's x squared, and then the outside 2 and the inside 2 would both be 5x, so that's 10x. And then 5 squared is 25. But then we're going to double all those, right? So we're going to multiply them all by 2. So actually that's going to make this 2x squared. It's going to make this, it's going to make this 20x. And it's going to make the 25, it's going to turn into 50. So I have to do the expanding first, then I multiply the 2 through. So it's doubling all this stuff. So we have this. Which now we can put the 7 and the 50 together. We could also bring the 3x and the 4 over to the same side. So, oops, I forgot that this is, okay, so here we go. So now I'm going to bring and put everything together. So let's see, subtract the 4 from both sides and subtract the 3x. I'm sorry, this is getting a little bit messy. But so my final equation would look like this, 2x squared. And then I have plus 17x. And then if I put the positive 7, the negative 4, and the 50 together, that makes plus 53. Now the problem with this one is, because I told you I tried it the other way, and it wasn't much easier, but this one is not factorable. So what's my choice? Quadratic formula. That's the best I can do. So we can remember our quadratic formula song, x equals opposite of b, plus or minus square root b squared, so 17 squared, which is 289. Actually, I'm going to do this whole discriminant, and it turns out to be negative 135. And then all over 2 times a, 2 times 2 is 4. So let's see if there's a biggest perfect square that's in 135. Let's see, 9 goes in there 15 times. So I could rewrite this as the square root of negative 1, the square root of 9, and the square root of 15. So my x is going to be equal to, there's 2 of them, negative 17 plus 3 square root of 15i over 4 and minus. So that's really, oops, I should say this plus or minus. It's easier to just write it as 1. Plus or minus. So then how do we go about finding the y's? Well, there is no real solutions anyway. So right away I should have just stopped. I shouldn't even have gone this far, but sometimes I get carried away when I'm doing quadratics. And I'm like, okay, see this right there? If that's a negative that we're taking the square root of, and we're talking about where do these graphs actually cross, well, if the solutions are non-real, they don't really cross. And so right away I could have just told right here when I saw that that was a negative square root that there are no solutions, so there are none. These graphs are never going to cross. They'll be those type like the last one we saw with the parabola and the line that, you know, just are completely separated from each other and never having a chance of crossing. So that was a lot of work for nothing, unfortunately. So the second one is kind of perfectly set up for substitution. I mean, it's not, none of these are really ideal. But what I could do is I could take what this one says y is equal to and put it right in the other equation right there for y. So let's see, that would look like this. 3x minus 2 times 1/4 times x minus 3 squared, okay, and then equals 13. So there's a lot of cleanup on this one. Not a lot of space on my paper for that, so I should have probably written a little bit smaller. So the first thing I could do is I could, combine the -2 and the 1/4 together, and that's going to make 3x minus, and then multiply those together, that makes -1/2. Oops, so it's actually not minus negative, it's actually -1/2, sorry. -1/2 times whatever when we expand this out, right? We expand that out, that would be x squared minus 6x plus 9. Oops. And then equals 13. So let's see if we can kind of put all this together now. So let's see, distribute the half through, so that's 3x minus 1/2 x squared plus 3x, because -1/2 I'm distributing through, right? And then minus 9/2 equals 13. Now, just a little strategy I might use right away here, just to kind of clean things up a little bit, is I want to take everything in here, and I'm going to multiply it by 2. Remember, that's legitimate as long as you do it to everything. And so I'm going to do that to get rid of the fractions, the 1/2. So that would make 6x. And then distributing the 2 to this part would just make this minus x squared. Actually, maybe I'll even multiply by -2. There's a thought. And then that way I can take care of that negative on that as well. So that would make this, oops, boy, I'm not having a great time with my stylus today. That'd make that -6. That'd make that plus x squared. That'd make this minus 6x when I distribute it to this, right? I'm distributing it to everything right there. And then distributing to this would make this a plus 9 equals 13. So now it's starting to kind of shape up. So now put everything on the same side. So we've got the x squared minus 12x. We had the plus 9, but if we subtract the 13, 9 minus 13 is -4, and that equals 0. Oops, I just noticed one thing. Oh my goodness, I'm having a rough day today. Oh gosh, so forgive me. If it were more possible to do this, I would just get rid of this part of the video and redo it. But anyway, I forgot to multiply the -2 by the 13, so that's -26. So I should be adding 26 to both sides. Sorry about that. So, oh my goodness, that's terrible. So that actually is going to make this into, I have a 9 plus 26 is 35. Oh goodness, that's much better. Again, I'm very sorry. I know you probably have those days too, so it's fine. It's been a long day. I just taught with you guys all day, and I'm making a video. So I'm going to see if I can factor this. I'm pretty sure this is factorable, so I'm thinking factors of 35. They have to add up to -12, so -5 and -7 would work. All right, very good. So x equals -5, or x minus 5, excuse me, and -7. That means my two solutions are x equals 5 and y equals 7. Now, these are solutions, right? These are graphically, they would be two ordered pairs, so I need a y to go with each one of them. So what I'm going to have to do is separately plug those in, and I just got to figure out the easiest one to plug it into. So I'm going to go ahead and take the 5 here. I'm going to plug it in for x there. So let's see, that would be 5 minus 3, which is 2. 2 squared is 4. 4 times 1/4 is 1. So that's one of our ordered pairs right there. And now I'm going to also plug in x equals 7. So now I'm going to take that one, plug that in, and 7 goes in there. So that would be 7 minus 3, which is 4. 4 squared is 16. 16 times the 4th is 4. So the other ordered pair is 7, 4. So my solutions, although this was not easy to get to, are actually at least nice integer values. So 5, 1, and 7, 4. And you could graph those, putting them in, I have to solve the second one for y, but you could put them in the graphing calculator and verify that in fact they do share those two common points. And so maybe we ought to use these you try questions, your turns to just get and do a couple more together just to make sure we're good, with that. So let's see. So A, that looks like that one's not a bad one to do. We could probably do substitution to solve this one for y. So this would be y equals negative 2x plus 6. Actually, I don't think I want to do that one because with that, I'm going to end up having to plug that in and square the y. So maybe we'll just get rid of the x's first. Let's see. So if I took the whole top equation and multiplied it by negative 2, I'm going to do that instead. So that would be negative 2x plus 12 equals, let's see, negative 2 times negative 1/6 is positive 1/3 y squared. And then that way, when I take the bottom equation, which is 2x plus y equals 6, I can add these together, and my x's will cancel out. So those are going to cancel out. And I'm left with y plus 12 equals, oops, that was supposed to be a 1/3 y squared, equals 1/3 y squared plus 6. Now, even though these are y, they're quadratic equations, so get everything on the same side. So I'm going to kind of swing the y over and the 12 over, so that's going to make 1/3 y squared minus y, and then if I subtract 12, so I'm going to subtract y and subtract 12, that makes minus y and minus 6 equals 0. And then just a quick little trick that'll make things easier in case this is factorable. I'm going to instead multiply everything by 3, and then that way I can get rid of the 1/3. So 3 times 1/3, those cancel. That leaves me with y squared. 3 times minus y is minus 3y. 3 times minus 6 is minus 18, and then 3 times 0 is, of course, 0. So now I think this factors. I'm pretty sure that's a factorable one, so I could just factor, let's see, y, and I need two factors that are different signs that are going to multiply to negative 18 and add to negative 3, so that would be what, negative 6, positive 3. So my two y's are y is 6, and then y equals negative 3. Now I got to find an x to go with those. So the x that's going to go with this one I can find by taking that and substituting it into whichever I think is the easiest one, and I certainly think the easiest one is the bottom equation there. So plug that in there. That gives me 2x minus 3 equals 6, which then when I add the 3, that's 2x equals 9. So x equals 4.5, or 9/2. So that's not a great solution, but it at least is a finite decimal. So we've got one of our ordered pairs there. And then if I take and substitute in this other one, 6 in, so that's going to, oops, plug it in right there. If I have a 6 in there and I subtract the 6 from the other side, so it's going to look like this. 2x plus 6 equals 6. Subtract 6, that gives me 2x equals 0, and that means x must be 0. So the other ordered pair, so let me just write these ordered pairs at the top now. So we have 4.5 and negative 3. I've got this new stylus, and I'm sorry it works terribly. It's really causing me some problems today. And then 0, 6. All right, let's try our very last one. Let's wrap this up. So I think this one, I'm going to have to get rid of this. Okay, this one looks like it should be pretty easy to do with elimination. So I'm going to multiply the whole top by negative. Just in other words, just change the signs. So that whole top equation, I'm going to rewrite this so it'll be negative x plus y equals negative 7. And then that way the bottom equation can stay the same. But then the y's will be opposites of each other, right? So now I'm going to add So when I add them, I get x squared minus x, because I can't combine those together, but the y's cancel. And then negative 7 plus 7 is 0. Oh, that's not too bad at all. So remember, when we don't have a constant term, the only kind of solving we can do is factor out the greatest common factor. So take out an x, and that will leave me with x minus 1. And that means my two possible x values are 0 and x equals 1. And then all we have to do to find the y's to go along with them is substitute those in to the original equation. So if I plug 0 in for x, say right there, doesn't really matter where, but that would be 0 squared, which is 0, minus y equals 7, so it means negative y equals 7, so y must equal negative 7. So that's my one ordered pair is 0, negative 7. And then if instead I went ahead and substituted in negative 1, so I'm going to plug positive 1. Oh my goodness, that is terrible. I am really struggling today. So I put the 1 in there, so it would be 1 minus y equals 7. So then I'd have to subtract 1, which means minus y equals 6, and that means that y must be negative 6. So that means my other ordered pair is 1, negative 6. Well, I guess if nothing less, we've conveyed the fact that you start adding in to a system of equations some higher degree portions of it. So instead of just being two linear equations, now we have a linear equation and a parabola. We've also seen where we would down the road maybe see where we have a line and a circle, or maybe two parabolas, or a parabola and a circle. So they can get much, much more complicated. And, that's where really it's just so important to just be really careful with your work, but just to kind of be able to fall back on the basics of when we did have two just linear equations. So at least we know the process and how it works, even though as the numbers and the equations themselves get more complicated, we still have a foundational skill set that we can use of elimination, substitution, and graphing. So that does it for today's class. Thanks for bearing with me through all the craziness. See you in class.